Okay, so perhaps if we could, we might get started. I'll introduce Vincent. My name's James Bailey. I'm one of Vincent's supervisors, and Vincent's a PhD student from the University of Melbourne in Computing and Information Systems, and he's affiliated with the Optima ARC Training Centre. And Vincent's going to be talking to us today about his PhD project, which is being conducted in conjunction with industry partner Southeast Water, and it's looking at an area called Predict-then-Optimise, or Predict-then-Optimise, and being applied to water flow control. So over to you, Vincent, to tell us about what you've been researching.
Thanks for the introduction, James. So hi, everyone, and thank you for attending my presentation. And thank you, Optima, for the invitation to present today. So in this talk, I'd like to present to you an interesting optimization problem that is given by our industry partner, Southeast Water, and some of the strategies that we developed to solve it. So this is a joint work with James Bailey, Christopher Leckie, Peter Stokke, and David Bergman. First, I should mention that my talk is based on a paper that we recently published at the Constraint Programming Conference in August. And if you'd like to know more about our work after the presentation, you can access our paper by following this link. If you're listening to this talk from Melbourne, you're very lucky. You're very lucky to live in one of the most livable cities in the world. So you might wonder, what makes Melbourne a great city to live in? Well, perhaps one of the overlooked elements that will make your next trip enjoyable is the sewage network quality that is available in that country. Melbourne holds a world-class sewage system, but it wasn't always the case. So I would like to take you back in the history of Melbourne's sewage system. So back in the 19th century, you wouldn't want to be living in Melbourne. Restrooms were located at the back of the garden, with a door that opens on the lane, and wastewater was directly dumped on the streets, creating the non-so-pleasant nickname of Smellburn. In fact, you can actually find the relics of these doors when you walk through the multiple lanes of Melbourne. So Melbourne understand this problem, and in the 1800s, they tried to remediate with it. So we started to see slender boxes, that is an early form of toilets that were located at the end of the garden. And the third boxes contain large buckets, which were accessible from the laneway by the nightman. So the nightmen started their job after the dark and collected wastewater from the neighborhood. While the nightmen helped to keep cities safe from disease like the cholera or the typhoid, they had a bad reputation. So despite the hard work, the disease would still spread, and this issue was attributed to them. So finally, in 1897, the All England Hotel is the first property to be connected to the sewage system, therefore putting an end to Melbourne, and Melbourne becomes marvelous again. So I hope you now have a better understanding of the importance of a good sewage system. So there are two main types of sewage networks. The most common is gravity-fed. In a gravity-fed network, the wastewater from individual properties is carried along the main pipe to the treatment plant. So usually properties are located uphill and gravity does the job. So gravity-fed networks have many benefits. They are the most common type of network, and therefore they are well understood. They are also simple to operate. So as long as there is a slope in the right direction, gravity systems run themselves. However, they have high maintenance cost, as operators need to dig large holes in the street to repair broken or blocked pipes. And this maintenance has a big impact on the customer, as large portion of the street need to be closed. The second type of sewage networks is based on pressure sewer system. So a pressure sewer system is a network of pump stations that are used to collect and manage sewage from individual properties. Pressure sewer systems are used in areas with challenging topography, where the landscape is either very hilly or very flat, and in areas with regularly flood, or where it's impractical to install other types of sewage systems. So pressure sewer systems have a lower maintenance cost, as we need to dig smaller holes in the street. They also have a lower installation cost, as pipes can be smaller and buried shallower. They can be installed in challenging terrain, and they can easily be expanded. However, they are much more complex to operate than conventional gravity networks. So in this talk, we're going to focus on the second type of network. So the system is composed of a tank that is typically buried at the back of the house and connected to the main network in the streets. There's a controller that activates the pump that is located at the bottom of the tank. So in standard control systems, we simply wait until the tank reaches capacity and we begin pumping out. So the wastewater goes in the tank. And when it reaches the cadence set point or the maximal level, it triggers the pump and we start pumping out. The wastewater is flushed into the main network until it reaches the minimal level and the pump turns off. So we observe this cycle throughout the day. Such simple control leads to peaks in sewage flow in the morning and in the evening, corresponding to peak water usage in the properties. And sewer systems is always designed to handle the highest peak flow projected in the network. So therefore, reducing the highest peak flow allows for smaller pipes, smaller treatment plants, as well as less chemicals used during the treatment process. There's a huge incentive to reduce the highest peak flow. So we formulate the following problem. Can we selectively release the wastewater within the tanks at strategic times, such as the total output flow is smoothed out? So in other words, we want to determine the times at which each tank should be emptied so that the highest peak flow is minimized. So to determine the times at which the tank are flushed, we first need to determine the input flow. So what and how much goes in the tank. So we want to roll out all the previous decisions to pumping out that was made using the simple policy to retrieve the original input flow. So the tanks are equipped with sensors that measure the level of wastewater within the tank. Therefore, the amount of wastewater in the tank corresponds to the difference of two consecutive positive readings. So we discretize the inflows of hour-long time steps so that we can solve this problem using an optimization model. We chose an hour-long time step as we don't observe any overflow for the selected tanks. We formulate a first MIP model. So the level in the tank at time t corresponds to the level in the tank at time t-1 plus the inflow times our decision variable x. Do we empty the tank or not? We add a constraint such as the capacity of the tank is never exceeded. And we add a constraint to prevent the wear and tear of the pumps by pumping out a minimal amount of wastewater. So in practice, such model doesn't scale well because for large number of tanks, the solution space is very large and the constraints require exploring a large portion of the solution space. So we move to a packing formulation. So we can visualize the inflows as a stack of blocks that have a start time and height corresponding to the time and amount of wastewater entering the tank. The time steps correspond to the knapsacks. So each block can be packed in a knapsack during the time it is available. So we add the capacity of the tank. Here it is equal to 3. We define latest as the time at which the inflow must be emptied before exceeding capacity. So this can be easily pre-computed. So here inflow 1 must be emptied before time 4. Similarly, inflow 2 may be emptied before time 5. So during the search, we decide to empty the first inflow at time 3. So we define the following new constraint. If tank S is emptied at time t prime, then each inflow before t prime must be emptied by t prime. So from a physical point of view, we cannot have wastewater in 2 stages that is flushed out and that is remaining in the tank. Again, from a physical point of view, we cannot have inflow 4 being pumped out after inflow 5. So we define the following constraint to enforce that inflows are pumped out in order. So this is the full packing formulation. So far we defined a policy for pumping out. So because our decisions are made on predicted inflows, we observe a difference in the pumping out decisions based on the actual inflows. The decisions are automatically revised by the controller that only accepts visible decisions. That is, the system won't activate the pump if the tank is empty, and it will activate the pump if no decision for pumping out was generated. This corresponds to the normal controlling method. We then define a set of non-predictive strategies. The first one corresponds to the current operational strategy, and that is our baseline. So a tank S is only emptied when it reaches capacity. We also define a second strategy that is we empty each tank as soon as it has more than the minimal capacity. We also define a random strategy. So we compute the proportion of pumping out for each of the tank. We flip a coin, and if we are below this proportion, we empty the tank. And we also have the clairvoyant strategy, that is running the optimization model with the actual inflow data. So that is our target, which is the minimal maximum outflow possible we can get. For the predictive strategies, we first use complex predicting models to generate plausible inflows. The issue with such model is that they tend to the mean and they do not accurately represent the underlying optimization problem that follows. So we lose the crucial information, which is the time the flow is peaking. Instead, we use a simple predictive method, which is historical sampling by generating subsequence in the historical data. So we consider a sampling window, for example, 7 days here, and we use one of the sample as our forecast. We also define a robust strategy as the worst case scenario for the sampling window, which uses the maximum inflow for each time period over the sampling window. So we use real data from our industry partner, and this corresponds to around 4,000 tanks. The prediction difficulty here is that we are considering a holiday area. So there's a huge fluctuation in water usage per household when people move from house to house. So here we have the our results. So in blue, you have the baseline strategy and the alternative strategy. And we can see that in orange here, you have the clairvoyant, so that's our target. Our method managed to considerably reduce the peak flow. So here are the results in more details. So we have the maximum mean outflow and the standard deviation outflow for each of the strategies. And we can see that there's a considerable reduction in peak available compared to the current baseline. Interestingly, the alternative strategy, which is always mapping out when possible, does not do much better than the original strategy. We can observe that the random balancing is quite of an effective approach. Now comparing the historical sampling, we can see that historical sampling method consistently perform better at reducing the peak flow. But the advantage of the worst historical sampling method is that we can get more stable results with a lower standard deviation. So in conclusion, we introduced a novel practical problem from the water industry, which is controlling a pressure sewer system to reduce peak flow. We proposed two formulations, an off-the-shelf mid formulation and a packing formulation. And we showed that our optimization models can significantly reduce the peak outflow compared to the current operational approach. As future work, we plan to take into account more realistic features of the network, which is the distinct of the tanks from the sewer treatment plant. And from an optimization point of view, we plan to investigate decomposition approach such as column generation, since the tanks are only weakly coupled by the objective. And ultimately, we want to investigate end-to-end predict plus optimize approach. Thank you.